Next, we will focus on solving the elliptic equation. So this involves the numerical method, such as the finite difference method, okay, that we can use to transform it into algebra difference equation. So we will learn this later. And we will use the heater plate as our example. So this is the heater plate in 2D. So we have a x and y dimension here. Let us randomly choose an element or a small point on the plate that can be defined by delta x multiplied with delta y dimension. So we want to investigate what is the heat transfer happen within this region. So the incoming heat flux consists of Qx and Qy, okay, which is the heat flux in x and y dimension. So after they passing through this element, okay, the heat flux flow out is Qy plus the step size in y dimension, which is delta y, and also the Qx plus delta x. So you can see from these two equations, so these are the heat flux flow in, Qx, Qy, which is these two elements going inside the element, and then, okay, x plus delta x and y plus delta y is referred to these two items. So we know that over the time, okay, it will reach the steady state condition, so which means the heat flux flow in must be equal to the one flow out. So in this case, we can let this equal to the equation here, and we write the equation here, and we found that the delta z, which is the thickness, can be ignored, can be cancelled out. Then we collect the term for delta y and delta x, and then we multiply with negative, then we get this equation. So the previous equation is written here, and you will find that this form is same with the component here, where this can be found in the partial derivative for delta q over delta x and delta q over delta y. So if we divide the equation by delta y, this can be cancelled. So we divide this by delta y, and we divide by delta x. So this term can be cancelled. Okay. So we can see that, okay, this equation 1 is similar to the component here. So in this case, if we take the limit for the delta x approximate to 0, we can convert this term into negative delta q over delta x. So same thing can be done for the second component to obtain the delta q over delta y. So this is the result. From the Fourier heat law, we can link the heat flux to the temperature change over delta x. So in other words, okay, to find the heat flux in x direction with the notation Qx, okay, can be written into this formula. And for the heat flux in y direction, we change the dx into delta y. So the k pi is the coefficient for the heat transfer, and then k rho c, okay, the definition is given here. And for the T is the temperature, and H is the heat in calorie, V is the volume, so C is the heat capacity, and rho is the density of the material. So in this picture, it shows the graphical representation for the heat flux equation. So previously we showed you that I direction, okay, in x and y, so that we can change the I to any dimension, x and y. So for example, that in this direction, let the I to be x, so we have to change all the I to be x. So imagine you have a high temperature here, 100 degrees Celsius, and low temperature here, let's say 0. So let's say you have a bar and 100 at this corner and 0 at this corner. Okay, so you can predict that the heat will of course flow from somewhere hot to somewhere cold, right? So the direction of the heat flow should be in this direction. So if you want to find the gradient, okay, the temperature gradient dt over dx, so you need to find the slope. So the slope can be computed easily by the gradient. So 100 here, 0 here. So let's say we take the distance is from 0 to 10. So the gradient in this case is equal to 100, okay, here, minus 0 divided by 0 minus 10. So you get it to be some negative value, okay, negative 10 in total. So your delta t over delta x in this case is less than 0. So in this case, you obtain the delta t over delta x to be negative. So once you multiply the negative k prime, you will get the result in positive. So if you get positive heat flux, it means that the direction of the heat flow is moving from in the x direction, right? On the other hand, let's say you have a rod here and you hit it in the end here to be 100 degrees Celsius. So you call the thing here to be 0 degrees Celsius. And in this case, you compute the gradient. So the dt over dx. Okay, so let's say this is x direction. We want to compute it. So same approach. So the temperature here is 0. You minus with 100. And then the distance here is 0. You minus with 10. So in this case, you get positive gradient, okay, which is greater than 0. So once you get positive, you multiply with negative k prime, your heat flux is negative. So what does it help? So if you get the heat flux Qx is negative, it means that the heat flux is moving in the opposite direction to the x-axis, right? So in simple, if let's say you have a beam and then you hit it here 100 degrees Celsius and cool it here 0 degrees Celsius, okay, and you define it to be x direction, okay, in this way. So where is the direction for the heat flux? So of course, okay, based on this high temperature, we expect the heat to flow from this point, okay, at 100 degrees Celsius to 0 degrees Celsius. So this is the direction for our heat flux, Qx, right? So in other words, okay, when you compute this, you should get it in positive value. Okay, it means it's in the same direction with x direction. How if let's say you have the beam, but in this case you have 0 degrees Celsius here and 100 degrees Celsius here. So of course the heat will flow in opposite direction. And let's say your dimension for x is still remain the same. So in this case, your Qx should be equal to negative value, indicating the heat flow is opposite to the x dimension. So these are the equations that we obtained so far: the heat flux in x direction, y direction, and the PDE. So if we differentiate Q with respect to x-axis, okay, we obtain this d squared over dx squared. And of course, we do the same thing here with respect to y-axis. Okay, this can be differentiated as well. So from here, you can see we can substitute inside this equation. And for this one, we can do the same thing. So with that, we obtain k prime negative can be cancelled, become positive there. So delta t over delta x. So negative multiply negative become positive. So k prime, so it's still the same, I can take out. So delta t over delta y. So don't forget the power of 2. Okay. So this can be equal to 0. So k prime is coefficient, it cannot be equal to 0. So therefore, this term must be equal to 0. So with that, we obtain the Laplace equation. So in this case, on the right hand side, when it's equal to 0, it means that the forcing function acting on this system is 0. This is known as homogeneous problem. So if let's say this is non-zero, like this, okay, so you have a function, okay, and your forcing function is some sort of for heat transfer, okay, heating system, so it can be a source, okay, or the sink of the heat. So in this case, this is known as Poisson equation. So with that, we have done the derivation of the PDE. So next, we are going to use the numerical method to solve this problem, to obtain the t in respect with respect to the x and y.